Today I am going to tell some few concepts about Module 2 Time Domain Analysis. So this is the Module 2. In control systems we are going to study about in detail the concepts on time domain analysis. According to the definition of the time domain analysis, we can see that whatever the response we are going to get when the input is changed with respect to the output is called as the response of the system. And this response we need to deal with respect to the time. Since the output is going to vary with respect to the input based upon the time, we are calling this to be the time response. So accordingly, the definition says that the time response of the system is the output response, which is the function of time when the input excitation is applied. That means when the output response is changing with respect to the input, when the time is changing is called as the time response. The time response of the system is divided into two types or divided into two parts, where we have two types of responses in the time domain analysis. One is called as the transient response and another one is called as the steady state response. Now first we need to understand what is this transient response and what do you mean by the steady state response. So you can see that mathematically we can write that whatever the time response is there, whatever the time response E of t is there, it is a combination or the summation of the transient time plus the steady state time. Now what is this CTT of t? The CTT of t is nothing but the transient response and CSS of t is nothing but the steady state response. Now the combination of this transient time as well as this steady state response will give us the time response, that is the entire definition. Now first let us understand what is coming under the transient response and what is coming under the steady state response. As the definition says here, the transient response is the part of the response which goes to zero as the time increases. That means if this is my graph, there will be a linear increase of the function and after some time it will be maximum. After that, whatever the input you give, there will be no change. So the response which goes to zero as the time increases mathematically is called as the transient response, and limit t tends to infinity, CTT of t is equivalent to 0 is the mathematical expression, because according to the definition we say that the response goes to 0 as the time increases. So here this is nothing but the steady state, this is nothing but a non-oscillatory response. Here I can also have an oscillatory response and the oscillatory response will be like this, and after some time it will go to 0. Whatever may be the increase with respect to the time t, I am not going to get an output which will be varying, but whatever the output is there, it will become 0 after some time as the time increases here. So mathematically we are saying that as t tends to infinity, the transient time will be equivalent to 0. As the time increases, it becomes 0. So we are giving the value of t to be equivalent to infinity and Ct of t will be equivalent to 0. Here you can see we have written here the transient response can either be an exponential response or it can be an oscillatory response. Now what do you mean by an exponential response? This is the graph which shows that there is an exponential increase. After exponential increase, whatever, even though you vary this, there will be no variation, the response will be equivalent to 0. What do you mean by second one, which is called as the oscillatory in nature? Oscillatory in nature is nothing but this waveform. So we can see that it is having a function with respect to a sine or cos. After some time, whatever the amplitude of this particular wave is there, the amplitude of this particular wave is becoming 0. It is becoming it is becoming constant. So this steady state response we can either find out by using an exponential response or by using an oscillatory response in nature. Next, what do we understand by the steady state? What is the definition of the steady state? The steady state response is the part of the total response after the transient has died. That means after this, you can see here, after some point, whatever we can see here, after some point, we told that this response will go to 0 as the time increases. Now after that also, there will be no change with respect to the output. So here we can see that it is becoming 0 and it will be 0 for a longer period of time. Here also the transient response will be 0 for a longer amount of time. Whatever this state is there, that is no change in the output that is happening. This state is called as the steady state state. Similarly, here we call it as the steady state state. So this part is called as the transient response. And whatever this part is there, this is called as the steady state part. Steady state part. So with this steady state, there is an additional term which is called as the steady state error. What is this steady state error? All of us know what is an error. Error is nothing but when an expected outcome we know, but still we are not going to get that expected outcome. Apart from that, we get some other values. For example, unity means we know that it is equivalent to 1. If when I give an input as a input and when I get an output, this particular output, whatever I am going to get, should be known well in advance. Now, when I know that output is equivalent to well in advance, but whenever I am measuring that in the real time, I am not getting that output to be equivalent to 1, but I may be getting a value which is lesser than that or which may be a greater than that, right? So suppose if 1 is the expected output I am supposed to get, I may be getting a value of 0.98 or I may be getting a value of 0.02. 1 was our expected outcome which was supposed to be present. But instead of that, I am getting here as 0.98 and 1.02. But 1.02 or 1.98, I cannot say that it is a completely negligible amount. But whatever this difference or the change with respect to the output is there with respect to 0.98 or with respect to the 1.02, this difference in value is called as the steady state error. This error is denoted by the term ESS, and this error will change with respect to the input that I am going to supply. The input can either be a unit step input, the input can either be a ramp input, or the input can either be a parabolic input. There are different types of standard test signals that are available. Depending upon these standard test signals, our error also will be changing. This steady state error part, whatever is there, we will see that in the subsequent slides. Now let us see what are the different types of standard test signals that are available. So here you can see the test signals for the time response. Now you can see here first function that we are going to study or we are going to see is called as the step function. So step function means what? Either it can come down or it can go up. It is just like a step. So we either climb the step or we will be at the same position. So it may be like this, a step function. Now if there is a step function, what will be the response is what we are supposed to see now. Now among the different types of the standard signals, the first type of signal that we are seeing is the step function. Now we have considered this particular diagram. In this particular diagram, let the switch be here, which is nothing but yes, and this switch yes can either be an open switch or it can be a closed switch. This output will be between the terminal 1 and 2. Now let us consider that whatever the voltage is there, that is nothing but K, be an independent voltage source, and this independent voltage source, let it be in series with the switch S. Now when this is the condition, and suppose I say that whatever the switch is there, the switch is said to be open switch, then what will be the output voltage at across the terminal 1 and 2? The output voltage across this terminal 1 and 2, when the switch is said to be open, is equivalent to 0. We know that. Why? Because here the switch is open. Since the switch is open, it becomes what? An open circuit. Since it is an open circuit, nothing is flowing between this particular 2 points. So when I say the switch is said to be a closed switch, when the switch is said to be a closed switch, whatever the output will be there between the terminal 1 and 2, that will be nothing but the output, the input voltage that I am going to supply. And if I say that this particular input voltage is K, when the switch yes when the switch S is equivalent to open, whatever the output voltage between the terminal 1 and 2 is there, that will be equivalent to K. And what is this K? This K is nothing but the input voltage that we are supplying towards this supply voltage. Now, at this particular condition, anyway we know that when S is equivalent to 0, the output is 0. No need to write the response for that. When the switch is said to be closed, we know that whatever the output voltage between the two terminals 1 and 2 is there, it will follow nothing but the supplied voltage, which is nothing but the K. Now, how do I draw the waveform for this? See, the x-axis is nothing but the time t and the y-axis is nothing but the voltage which is varying with respect to the time, and I name the y-axis to be V of t. Now, when it is equivalent to 1, that is when the switch is said to be equivalent to 1, the voltage between the terminal 1 and 2 is nothing but equivalent to this K. Therefore, what may be the response here? The response will be nothing but a constant line where this is equivalent to K. So, I can also write this as E of infinity, which is equivalent to 1, or I can say that it is following nothing but my input, which is equivalent to K. Now, how do I write this in the mathematical form? To write this in the mathematical form, what will be the output voltage? V of t will be equivalent to 0. At what conditions this V of t is equivalent to 0? We know that it is equivalent to 0 when the switch is said to be the open switch. So, I consider the condition of t between minus infinity to 0. When the condition between minus infinity to 0 is there, at the time t is equivalent to 0, whatever the output voltage is there between 0 to infinity will be equivalent to K. Now, if I combine these two equations, then I will be getting V of 2 is equivalent to 0 when the switch is said to be equivalent to closed, and V of t will be equivalent to K when the switch is said to be a closed switch, and V of t will be equivalent to 0 when the switch is said to be an open switch. So, your t varies from minus infinity to plus infinity. So, first condition is between minus infinity to 0, that is when the switch is said to be in the closed open path. When it is open, whatever the output voltage is there, the output voltage will be equivalent to 0. When it is between 0 and greater than 0, that is it will be increasing until infinity, then what will be the output voltage? That means the switch is said to be the closed switch. When the switch is said to be the closed switch, whatever the input voltage we supplied, we will be getting back the same input voltage. Therefore, my V of t will be equivalent to K. Therefore, by seeing these equations, what can I conclude? The conclusion that I can make is unit step function is denoted by U of t, and it is defined as U of t, that is the unit step function, is equivalent to 0 for all the values of t which will be lesser than or equivalent to 0, and the same unit function will be equivalent to 1 when t will be greater than or equivalent to 0. This is the mathematical equation. Now, whatever the equation that we have got, we need to get the final response of that particular system. In order to get the final response of that particular system, I need to convert whatever was in the time domain into the Laplace transform. So, the Laplace transform for this function f of t will be given by the equation integration over the limit 0 to infinity u of t into e to the power of minus st into dt. But what is u of t equal to? U of t we have already seen in the previous slide that u of t will be equivalent to 1 for t greater than or equivalent to 0. So, the u of t value that I will be substituting in this equation will be equivalent to 1. 1 into e to the power of minus st into dt. Why am I writing this e to the power of minus st into dt? Because I told that the waveform is said to be an exponentially increasing waveform. I did not consider the waveform which is said to be oscillatory in nature. Here I considered the waveform which is said to be exponentially in nature. Therefore, 1 into e to the power of minus st into dt. Now let us perform the integration of this. When I perform the integration of this, 1 into e to the power of st will be equivalent to e to the power of minus st only. Therefore, now what I have to do is I need to just perform the integration with respect to e to the power of minus st. What is integration of e to the power of x? Integration of e to the power of x is e to the power of x divided by x, with the same limits whatever I have given. So, e to the power of minus st divided by minus s with the limits 0 and infinity. Now, when I substitute the limits here, that is upper limit minus the lower limit, I will be getting the value which is equivalent to 1 divided by s. Now, whenever I say that I have a function which is said to be a unit step function, then I need to substitute the value as 1 divided by s. So, what is the final conclusion with respect to the step function? With respect to the step function, the final conclusion is whenever I use a unit step function, after the integration, applying the upper and the lower limits, whatever the value that I will be getting is nothing but 1 divided by s. Whenever I say the input is said to be a unit step input, then we can substitute the value as 1 divided by s. So, this is nothing but the first standard function or this input. Now, let us move on to the second function or the second standard input. What is this second function or the second standard input? Now, let us see the second one, which is called as the ramp function. Now, instead of the step function, now let us consider the ramp function. Now, let us see what is the definition of this ramp function. What is the ramp function telling you? The ramp function starts from the origin, increases or decreases linearly with respect to the time t. Here, let r of t be the ramp function. This function is called as the ramp function, and this is nothing but the time which is varying with respect to the time t. So, we can say that ramp function starts from origin. That means this is nothing but my origin. This is the point with respect to the origin. It starts from the origin. It either goes up, it either increases or it can either decrease. If this decreases, then this is how I will be getting the waveform here, where this is nothing but t and this is nothing but my r of t function, right? So, increasing is this function and decreasing is this particular waveform. So, here either it can decrease or increase linearly with respect to the time. Since it is saying linearly, we are drawing this as a straight line. So, if it was exponential increase, whatever we did in the previous function, we will be doing that one. So, let r of t be the ramp function. Now, what is the final conclusion here? The final conclusion is r of t is equivalent to 0 for t lesser than equivalent, for t lesser than 0. That means what? This is the point which is equivalent to 0. Lesser than this, anything which is from this particular side, I am not getting any value here because it is still at 0. It starts at 0. So, whatever is the lesser value, that r of t is said to be equivalent to 0 for the time t lesser than 0. Suppose if the time t is greater than 0, what is the equation that we will be getting? This will be a constant k, and here we are telling that the value of k is said to be greater than 0. That means the constant k which will be varying with respect to the time t for t greater than 0. Now, suppose if I want to write or bring that into the normal function, we did for the first one, that is nothing but the step function, then again I have to take the Laplace transform of this. When I take the Laplace transform of this particular function, we can see that 0 to infinity, what type of input we are giving here? I am not giving a unit step one, because you can see here in the previous one we wrote here as u of t. But here we are giving the input to be what? The type of input that we are going to give here is a ramp input. Since ramp input is there, the definition, the mathematical equation becomes integration 0 to infinity r of t into e to the power of minus st into dt. But what is this r of t? This r of t we have already got here, that is for t greater than 0. The value of r of t is nothing but kt. So, I am substituting k into t e to the power of minus st into dt. Now, let us assume that the value of k is nothing but a constant one. I will bring this constant outside. Now, whenever integration is there with respect to two terms, we know how to do that by using parts method. By using the parts method, I will be getting the final answer for the ramp as k divided by s square. Now we can see the difference, that whatever my input r of s is there, the r of s, if I say that it is equivalent to what? A type of function which is said to be a ramp function, then I can substitute in this place as k divided by s square. Now just compare this with the previous one. That is nothing but the step 1. So what did we get in the case of the step? In the case of the step, I got the output as 1 divided by s. But in the case of the ramp function, I am getting the output as 1 divided by s square. Now here you can see, for unit ramp, when the value of k is equivalent to 1, that is for k lesser than 0, this is the ramp function that I will be getting. That is the negative ramp function I will be getting here. Next, coming to the third one. So we will recall 1 divided by s is what we got for the function if the input is said to be a unit one. 1 divided by s square I will be getting if my function is said to be what? A ramp function. If this is 1 by s and if this is 1 by s square, now we can just guess what may be the output that I will be getting if the function is said to be a parabolic function. So obviously, as our guess, it is 1 divided by s cube. Now how are we getting this 1 divided by s cube? Let us see now. Let us see what is the definition. The value of r of t is 0 for t lesser than 0 and is a quadratic function for t greater than 0. So you have seen in the previous two cases, for lesser than 0 and for the greater than 0. What are the two cases that were there? In the similar manner now, in the parabolic function also, if the t value is lesser than 0, whatever the r of t value is there, that r of t value is said to be equivalent to 0. Suppose if the value of t is greater than 0, what type of function we will be considering? The type of function that we will be considering is said to be a quadratic function. Now this parabolic function represents a signal that is one order faster than that of the ramp function. So you can see here, this ramp function was one order faster than that of the step. The parabolic is one order faster when compared to that of your ramp and 2 orders faster when compared to that of your unit step. Now let us, according to this particular definition, let us write the mathematical equation. So what is the equation that we will be writing for t lesser than 0? For t lesser than 0, we are saying that the value of r of t is said to be equivalent to 0. Therefore, I can write that as r of t is equal to 0. Next, what for t greater than 0, what am I saying? I need to consider that as a quadratic function. So this quadratic function can be written as k divided by 2 into t square. K divided by 2 into t square, where t will be greater than 0. Suppose if the parabolic function is said to be a unit parabolic function, that means the value of k is equivalent to 1. When the value of k is equivalent to 1, anyway for t lesser than 0, r of t was 0, it doesn't affect, therefore I will be rewriting the same equation there. But if t is greater than 0, what is the value of r of t? K into t square divided by 1. But I am considering here to be a unit parabolic function. Since it is a unique parabolic function, what is the value of k here? The value of k is said to be equivalent to 1. Since the value of k is said to be equivalent to 1, here I will be writing the r of t function as t square by 1 because k into t square divided by 2, where k is equivalent to 1 into t square divided by 2. That means 1 into t square will be equivalent to t only, therefore it is t square divided by 2. So for t lesser than 0, it is 0, and for t greater than 0, the parabolic function is said to be t square divided by. Now same thing, we need to again take the Laplace transform of whatever we have function. So what is the function that I am considering now? The type of function that I am considering is a ramp function here. So the ramp function is denoted by r of t. So 0 to infinity integral r of t into e to the power of minus st into dt. But what is r of t? From the previous slide, our r of t is how much? K into t square divided by 2. So k into t square divided by 2 into e to the power of minus st into dt. So now if I substitute this and if I consider again integration with respect to the parts method, I will be getting the value as k divided by s cube. Therefore, the final function with respect to the parabolic function is k divided by s cube. Now, according to the definition, for t lesser than 0, it is said to be equivalent to 0 because it will be moving this side. For t greater than 0, it is k into t square divided by 2 was the function, or here if I see it is s cube function. That means it will be increasing like this, which is nothing but the parabolic function. Now, coming to the fourth one, which is called as the impulse response, and this is the last type with respect to the standard signal. So here you can see I am going to considering this figure. So when I consider this figure, initial definition, what it says, the initial definition says that the first pulse has the width t. So I have a width t here at time t. And height as 1 divided by t. And what is the height of this particular function? The height of this function is nothing but 1 by t. And what is the area of the pulse? The area of the pulse, let us consider that to be equivalent to 1. Now what I am going to do is, I make a half of this particular function. When I make a half of this particular function, what will be the value of t? T will be divided by 2, therefore it is t divided by 2. Now 1 by t, if I perform half of that function, then you know that it is 1 divided by t. If I again half that particular function, then this 2 will go to the numerator, therefore it will be equivalent to how much? 2 divided by t. So this is the place which is nothing but 2 divided by t. Now whether it is 0 to t with 1 by t or 0 to 2 by t, t by 2 with 2 divided by t, what is the area? The area is still said to be equivalent to unity only. Either you consider this, or if I consider this, here also it has an area of 1 and here also it has an area of 1. So under such a circumstance, the type of response that we will be getting is called as what? The type of response that I will be getting is called as an impulse response. Now how do I draw the waveform for this impulse response? The waveform for this impulse response is like this. Okay, so this is varying with respect to the time t, and here it is nothing but an impulse function, that is nothing but delta function. So at 0 you will be getting a unity function like this. That means the area under the curve is said to be equivalent to 1 always. So how do I write it? So we can say that the duration of the pulse approaches 0, the amplitude approaches infinity, but still the area of the pulse is said to be unit. So what is the definition of an impulse? The pulse for which the duration tends to 0 and amplitude tends to infinity is called as an impulse function. This impulse function is denoted by what function? It will be denoted by my delta function. So I can write this mathematically as delta t is equivalent to 0 when t is not equivalent to 0. Why am I writing this as t is not equivalent to 0? If you just check this particular waveform, only at 0 you are having an output. Apart from that, all the other values, either positive side or towards the negative side, I don't have any output. Therefore, only at t is equivalent to 0, I will be getting an infinity value. Whenever t is not equivalent to 0 as this condition, what is the delta function here? The delta function is said to be equivalent to 1. So, the impulse function has 0 value everywhere except at t is equivalent to 1, and at t is equivalent to 0, the amplitude also is said to be an infinite amplitude.